Welcome back to Chapter 3 of Principles of Mathematical Analysis. So far we have studied convergent sequences, subsequences, Cauchy sequences, and upper and lower limits. In this short but useful section, we step back from the abstract theory and compute the limits of 5 sequences that show up again and again in analysis. The 5 limits collected in Theorem 320 are the workhorses we will reach for in the rest of the chapter, especially when we test series for convergence. Every proof relies on a single simple bounding principle, which we will isolate first and then apply 5 times. Here is the plan. We open with a brief motivation, why these particular sequences deserve their own section. We then assemble 2 tools, the squeeze principle, a simple bounding remark, and the binomial theorem, which we build up carefully and prove. Next, we state Theorem 320 with its 5 parts. After that, we walk through the proofs one by one. Part A is a direct application of the Archimedean property. Parts B and C rely on the binomial theorem. Part D extends the binomial idea to higher powers, and Part E is then a one-line consequence. We close with a summary and a look ahead to series. Up to this point, the chapter has been mostly abstract. We defined what it means for a sequence to converge, what a Cauchy sequence is, what the upper and lower limits are. We have very few concrete sequences in our toolkit yet. But certain concrete sequences appear so often that they deserve to be in our muscle memory. Expressions like 1 over n, the n, the root of a constant, the n, the root of n, or powers of a number less than 1 in absolute value, show up over and over again in proofs. Our goal in this section is to pin down the limits of 5 such sequences, once and for all. After this short section, we will treat the answers as known facts and quote them freely. Doing the work here, in one place, saves us from repeating the same binomial estimates in the chapters to come. One more point is worth flagging up front. All 5 proofs share a single tool, a simple squeeze. If we can bound a non-negative sequence above by something that visibly goes to 0, then our sequence also goes to 0. That is the entire engine. We will isolate it first and then just apply it 5 times. Here's the bounding remark in precise form. Suppose we have a non-negative sequence, x sub n, that is dominated past some index by a sequence s sub n that we already know goes to 0. Then x sub n also goes to 0. The proof is one line. Given any positive epsilon, since s sub n goes to 0, we can find an index past which s sub n is less than epsilon. From that index on, our sequence x sub n is squeezed between 0 and epsilon, which is exactly the definition of converging to 0. Here's the picture behind the squeeze. The horizontal axis is the index n, and it is now marked with ticks at the whole numbers 1, 2, 3, and onward, to stress that we are working with a sequence and not a continuous function. The vertical axis is the value. The brown dots are the dominating sequence s sub n. The faint brown curve through them is just a visual guide. The blue dots are our sequence x sub n. At every index, the blue dot lies below the brown dot, inside the shaded band between 0 and s sub n. As the brown dots collapse onto the horizontal axis, the blue dots have nowhere to go but down to 0 with them. That is the squeeze in one picture. Next, we gather a second tool, the binomial theorem, which will supply the bounds we feed into this squeeze. The binomial theorem rests on the binomial coefficient, and the binomial coefficient is in turn built from factorials. So we start at the bottom with the factorial itself. For a whole number n, at least 1, n factorial is the product n times n minus 1 times n minus 2, and so on down to 1. By convention, 0 factorial is 1. Like the binomial coefficient to come, the factorial has a counting meaning, shown in the red block. N factorial is the number of permutations of the set 1 through n. That is, the number of ways to arrange n distinct objects in a row. The reason is a quick choice count. N objects could go in the first slot, then n minus 1 remained for the second, and so on, until a single object is left for the last. Multiplying the choices gives n factorial. Let us make this concrete with n equal to 3. The slide shows a tree of all the permutations of the set 1, 2, 3. Reading from the top, the node marked start branches 3 ways, one for each choice of the first entry. From each of those, the tree branches 2 ways, for the 2 elements still available for the second entry. Finally, only 1 element is left, and it fills the third entry. So the bottom row, in amber, lists the 6 complete arrangements. Counting the branches level by level, 3 times 2 times 1 equals 3 factorial, which is 6. So there are exactly 6 ways to order 3 objects, just as the formula predicts. With the factorial defined, we can introduce the binomial coefficient. By definition, n choose k is a product of k consecutive integers, n times n minus 1, down to n minus k plus 1, all divided by k factorial. As the slide shows, this equals n factorial over k, factorial times n minus k factorial. Either way, the formula carries a concrete meaning, stated in the red block. N, choose k, is exactly the number of k element subsets you can form from a set of n things. On the next slide, we prove that the formula and this meaning agree, using a counting argument. Here is the counting argument. We count one and the same collection, the ordered k tuples of distinct elements drawn from the numbers 1 through n in 2 different ways. Write C for the number of k's in element subsets. That is the quantity we want to identify. First, count the tuples directly. There are n choices for the first entry, then n minus 1 for the second, since 1 element is now used up, and so on down to n minus k plus 1 for the last entry. Multiplying these gives n factorial over n minus k factorial. Second, count the tuples by grouping. Every tuple comes from choosing a k element subset and then ordering it. There are c subsets, and each can be ordered in k factorial ways. So this count is c times k factorial. The 2 counts describe the same collection, so they are equal. Dividing by k factorial isolates c, and it equals n factorial. Divided by k factorial times n minus k factorial, which is exactly n choose k. The formula and the meaning agree. The next slide works through a concrete case. Let us see the counting proof in action. With n equal to 4 and k equal to 2, we want the number of 2 element subsets of the set 1 through 4. Following the proof, we count the ordered pairs of distinct elements 2 ways. Counting directly, there are 4 choices for the first entry and 3 for the second, giving 12 ordered pairs. That is 4 factorial over 2 factorial. The slide groups those same 12 pairs into 6 boxes, 1 box per 2 element subset. Each subset, shown in blue, sits above its 2 orderings, shown in amber. For instance, the subset containing 1 and 2 accounts for the pair 1 then 2, and the pair 2 then 1. Since every subset contributes exactly 2 factorial, which is 2, ordered pairs, the number of subsets is 12 divided by 2 factorial, which is 6. And 6 is exactly 4, choose 2. The general formula and the concrete count agree. With the binomial coefficient defined and understood, we can state the binomial theorem itself. It expands a power of a sum, a plus b, raised to the mon, the power, becomes a sum of n plus 1 terms, and the k, the term, is the binomial coefficient n choose k, which we just studied, times a to the n minus k, times b to the k. One small notational point. When a or b is 0, the formula produces a term with 0 raised to the 0 power, which is normally left undefined. Throughout the binomial theorem, we simply adopt the convention that 0 to the 0 power equals 1. That keeps every term meaningful and the formula correct even in boundary cases, such as a plus 0 raised to the n, the power, which should of course equal a to the n. One identity our induction proof will lean on is Pascal's rule, n plus 1 choose k equals n choose k plus n choose k minus 1. Here is a short counting proof. The left side, n plus 1 choose k, counts the k element subsets of the whole numbers 1 through n plus 1. We sort those subsets into 2 piles by whether or not they contain the largest number, n plus 1. A subset that leaves n plus 1 out is simply a k element subset of 1 through n, and there are n choose k of those. A subset that includes n plus 1 is that number adjoined to a k minus 1 element subset of 1 through n, and there are n choose k minus 1 of those. The 2 piles are disjoint and together account for every subset, so adding their counts gives n choose k plus n choose k minus 1. That is Pascal's rule. We prove the binomial theorem by induction on n. The base case is n equals 0. Both sides are simply 1, so the formula holds. For the inductive step, assume the formula holds for some n. To reach n plus 1, we write a plus b to the n plus 1 as a plus b times a plus b to the n, and substitute the inductive hypothesis. Multiplying that sum through by a and separately by b produces the 2 sums on the slide. In the left sum, every power of a has gone up by 1. In the right sum, every power of b has gone up by 1. Next, we line these 2 sums up term by term. Now we collect, for each k, the coefficient of a to the n plus 1 minus k times b to the k. First, we reindex the right sum, replacing k by k minus 1, so that it runs over k from 1 up to n plus 1. 2 terms sit at the ends and come from one sum only. At k equals 0, only the left sum contributes. Its term is n choose 0 times a to the n plus 1. Since n choose 0 and n plus 1 choose 0 are both equal to 1, that coefficient already equals n plus 1 choose 0. At k equals n plus 1, only the right sum contributes. Its term is n choose n times b to the n plus 1. Since n choose n and n plus 1 choose n plus 1 are both 1, that coefficient already equals n plus 1 choose n plus 1. So both endpoint coefficients are already in the form we want. The remaining terms are the middle ones, where k runs from 1 to n. For each such k, both sums contribute. The left sum with coefficient n choose k, and the reindexed right sum with coefficient n choose k minus 1. Pascal's rule says these add up to n plus 1 choose k. So at the endpoints and in the middle alike, every coefficient equals n plus 1 choose k. The 2 sums have collapsed into the single binomial formula with n replaced by n plus 1. which closes the induction. The binomial theorem is proved. The next slide records a second proof, a purely combinatorial one that is worth seeing. Besides the induction, the binomial theorem has a slick combinatorial proof. Write a plus b to the n, the power, as a product of n copies of a plus b. Multiplying out, every term pulls one letter, a or b, from each factor. The diagram shows the case n equals 5. The 5 factors are in a row, numbered 1 through 5. For one term, the chosen letter in each factor is circled, a from factors 1 and 3 in blue, and b from factors 2, 4, and 5 in amber. Multiplying the circled letters gives a squared times b cubed. The letter b was taken from the factor set containing 2, 4, and 5. Here's the punchline. A term equals a squared times b cubed exactly when b is chosen from 3 of the 5 factors, that is, from a 3-element subset of 1 through 5. There are 5 choose, 3 or 10 such subsets, so that is the coefficient of a squared times b cubed. The same reasoning with k factors giving b shows the coefficient of a to the n minus k times b to the k is n choose k, which is the binomial theorem. With both tools in hand, the squeeze principle and the binomial theorem, we are ready to state the 5 special limits. Now we reach the main result of the section. Theorem 320 collects 5 limits, and we will build the statement one part at a time, so we can talk about each. Part A says if p is any positive real number, then 1 over n to the p goes to 0 as n goes to infinity. For p equal to 1, this is the familiar fact that 1 over n tends to 0. The theorem extends it to any positive power, including fractional powers like 1/2, where the sequence is 1 over the square root of n. Part B says the en, the root of any positive real number, tends to 1. So the cube root of 2, the 10th root of 2, the 100th root of 2, and so on, march steadily toward 1 from above. And the same is true from below, if we start with a positive number less than 1. This is a surprising fact when you first meet it, because the n, the root of, say, 1,000,000, still ends up close to 1 once n is large enough. Part C is even more striking. It says the n, the root of n itself, tends to 1. Here the input is no longer a fixed positive number, but the index n, which is growing without bound. Even so, the n-th root grows slowly enough to stay arbitrarily close to 1. This is one of the most useful concrete limits in analysis, and it underpins the root test we will see in a few sections. Part D is the most powerful of the 5. It says that any polynomial style growth in n, written as n to the power alpha for any real alpha, is eventually crushed by exponential growth in the denominator, written as 1 plus p raised to the nth power, whenever p is positive. In short, exponentials beat polynomials. Note that alpha is allowed to be any real number, so even huge powers like n to the millionth are eventually dominated. Part E rounds out the list. It says that any number x whose absolute value is strictly less than 1 has powers that tend to 0. For example, 1/2 to the EGN goes to 0, and so does minus 0.9 to the EGN. This is the geometric decay we will lean on heavily when we start studying series. As we will see, Part E falls out of Part D with almost no work. We want to show that for every positive epsilon, we can find an index past which 1 over n to the p is less than epsilon. To arrange this, we solve the inequality 1 over n to the p is less than epsilon for n, obtaining n greater than 1 over epsilon, all raised to the power 1 over p. The Archimedean property of the real numbers, recalled from Chapter 1, says that such an n exists no matter how large the right-hand side is. Once we have an index n exceeding that threshold, raising both sides of the inequality to the power p gives n to the p greater than 1 over epsilon. Taking reciprocals flips the inequality, so 1 over n to the p is less than epsilon. That is precisely what we needed, so the limit is 0. The strategy is to write the n, the root of p, as 1 plus a small correction x sub n, and then show that the correction shrinks to 0. We begin with the case p greater than 1, so x sub n is strictly positive. Step 1 is the key estimate. 1 plus x sub n raised to the n the power is at least 1 plus n times x sub n, and the left side equals p by the definition of x sub n. The remark below proves this estimate from the binomial theorem we established earlier. Expanding 1 plus x raised to the ending n, its power gives 1 plus n times x plus n. Choose 2 times x squared and onward. When x is non-negative, every term is non-negative, so dropping all but the first 2 only decreases the sum, leaving 1 plus n times x. This estimate is known as Bernoulli's inequality, and it will return later. Step 2 turns Step 1 into an explicit handle on x sub n. Step 1 says p is at least 1 plus n times x sub n. Subtract 1 from each side, then divide by the positive number n, and out comes the bound on the slide. X sub is positive, and at most p minus 1 divided by n. The point of this step is that we now have a concrete upper bound, one we can squeeze in a moment. Step 3 applies the squeeze. The upper bound equals p minus 1, a fixed constant, times 1 over n. By part A of Theorem 3.20, 1 over n goes to 0, so the whole bound does too. The squeeze remark then forces x sub n to 0, and adding back the 1, the n, the root of p, tends to 1. The case is done. 2 cases remain. If p equals 1, the n, the root of 1, is always 1, so the limit is trivially 1. If p is strictly between 0 and 1, let q be 1 over p, which is greater than 1. By the case we already proved, the n, th root of q, tends to 1, but the n, the root of p, is just 1 over the n, the root of q, and 1 divided by something going to 1 also goes to 1. That finishes Part B. The strategy mirrors Part B. We write the n, the root of n, as 1 plus a non-negative correction, x sub n, and aim to squeeze x sub n to 0. The catch is that n itself grows without bound, so the linear bound from Part B is too weak. We need a quadratic term. Step 1 keeps the term with binomial coefficient n, choose 2, which equals n times n, minus 1, all over 2, times x sub n squared. The left-hand side is n, because the n, the root of n raised to the n, the power is n. The remark below spells out why we may keep just that one term. The binomial theorem writes 1 plus x raised to the n, the power as a sum over k of n, choose k, times x to the k. When x is non-negative, every term in that sum is non-negative, so the whole sum is at least any single term we choose to keep. Here we keep the k equals 2 term, and that gives the bound on the slide. Step 2 isolates x sub n, exactly as we did in Part B. Dividing the binomial bound through by n times n minus 1 over 2 gives x sub n squared is at most 2 over n minus 1. Taking square roots gives the bound on the slide. X sub n is non-negative, and at most the square root of 2 over n minus 1. Again, the aim was an explicit upper bound that visibly shrinks to 0, and now we have one. Step 3 applies the squeeze. 2 over n minus 1 goes to 0 by part A, and taking square roots preserves the limit, so the upper envelope on the slide also goes to 0. The squeeze remark then forces x sub n to 0. Adding back the 1, the nth root of n tends to 1, finishing part C. Here is a numerical picture of parts B and C. The horizontal axis is the index n, and the vertical axis is the value. The blue curve is the n, the root of 2, an example of part B. It starts above 1 at small n and decreases toward 1. The red curve is the n, the root of n, from part C. It rises briefly because for small n it can exceed the blue curve, but very quickly it also bends back down toward 1. The orange dashed line is the asymptote at value 1, which both curves approach as n grows. For part D, the heart of the argument is to bound the exponential 1 plus p raised to the n's power below by a polynomial in n of degree higher than alpha. The setup line fixes an integer k strictly greater than alpha and also positive. This k is the degree of that polynomial. Step 1 expands the exponential via the binomial theorem and keeps only the kth term, which equals n choose k times p to the k. The binomial coefficient is a product of k consecutive integers from n down to n minus k plus 1, divided by k factorial. For n exceeding twice k, each of those integers is at least n over 2, so the product exceeds n to the k, divided by 2 to the k. This delivers the cleaner lower bound on the right. Step 2 just divides. The numerator is n to the alpha, and the denominator is bounded below by n to the k times p to the k, divided by 2 to the k times k factorial. Inverting and multiplying gives the bound on the slide. The ratio is less than a fixed positive constant times n raised to the power alpha minus k. The key point is that alpha minus k is strictly negative, because we chose k larger than alpha, so the variable factor is a power of n with a negative exponent. Step 3 finishes the proof. Writing alpha minus k as the negative of a positive number q, the variable factor n to the alpha minus k is the same as 1 over n to the q, which goes to 0 by part C. So the right-hand side of the bound, a fixed constant times this vanishing factor, goes to 0. The squeeze remark applies once more, and the original ratio goes to 0. That settles part D. Here is the picture behind part D with p set to 1/2, so the denominator is 1.5 to the n. The horizontal axis is the index n, and the vertical axis is the ratio n to the alpha over 1.5 to the n. The blue curve is the case alpha equals 2. The red curve is alpha equals 4. The alpha equals 2 ratio is naturally much smaller, so we scaled the blue curve up by a factor of 50 to make the two comparable in one frame. The red curve is shown at true size. Both curves tell the same story. Each rises for a while, reaches a peak, and then collapses toward 0. No matter how large alpha is, the exponential growth in the denominator eventually overwhelms the polynomial growth on top. Part E is a one-line consequence of part D, but we need to set up the right substitution. Suppose the absolute value of x is strictly less than 1. If x is 0, every power is 0, and we are done. Otherwise, write the absolute value of x as 1 over 1 plus some positive number p. This is always possible because by hypothesis the reciprocal of the absolute value of x exceeds 1. So subtracting 1 leaves a positive number. The absolute value of x to the 8n is 1 over 1 plus p raised to the n the power, which equals n to the 0 over 1 plus p raised to the nth power. That is exactly the expression in part D with alpha set to 0. By part D, it goes to 0, since the absolute value of x to the n goes to 0. X to the n itself goes to 0. That completes the proof of Theorem 3.20. Let us recap. The first of our two tools is the squeeze. If a sequence is sandwiched between 0 and another sequence that goes to 0, then it goes to 0 too. That simple remark is the engine behind every proof. The second tool is the binomial theorem. It expands a plus b to the n, the power, as a sum of binomial coefficient terms. We proved it by induction, and the key identity driving that induction was Pascal's rule, which says n plus 1 choose k equals n choose k plus n choose k minus 1. The binomial theorem is what supplies the bounds we then feed into the squeeze. Part A of Theorem 320 says that 1 over n to the p tends to 0 for every positive power p. This is the workhorse for everything that follows. Parts B and C record two perhaps surprising root limits. The nth root of a positive constant tends to 1, and so does the nth root of n itself. Both proofs followed the same pattern. Write the root as 1 plus a small correction, bound the correction by the binomial theorem, and squeeze. Part D is the most powerful entry on the list. It says that exponential growth in the denominator overwhelms any polynomial-style growth in the numerator. This is the slogan to keep in mind. Exponentials beat polynomials. It will show up again every time we compare growth rates. Finally, Part E gives the geometric decay we will use all the time, powers of any number whose absolute value is strictly less than 1 collapse to 0. This will be the backbone of the geometric series and the root and ratio tests. Coming up next, we turn from sequences to series. We define what it means for an infinite sum to converge, and we develop the standard tests, the Cauchy criterion for series, the comparison test, the root test, and the ratio test. Several of these tests lean directly on the 5 special limits we just established. So even though this section was short, its results will be in play for the rest of the chapter. See you in the next section.